Okay, so I'll get started. My name is Alex Khan. I've been in the IT industry for 25 years or so, and I had an interest in physics. I was actually a dual major in physics and engineering, and graduate from Purdue University. And since then, obviously, I was involved more in computers and automation and all of that. But in 2018, I saw that DWave had made their quantum computer available online with the LEAP program, and I actually signed up for the LEAP program in 2018 and started looking at it. And I will say that after so many years of not having done physics, it was very challenging. The mathematical part, the physics part was all very complicated, and I don't think I really understood it very well. And then I took a course with MIT on quantum computing and worked with with the Chicago quantum team that I'm working with right now. And it's only after working with the team and getting my hands dirty and looking at the problems did I begin to understand how does DWave really work. So what I wanted to do was to really start from the ground up and show to the community kind of how to think about DWave and how does it really work, how does it really solve problems, and again, feel free to ask questions. So I'm going to get started with a very basic model that everyone's familiar with. I'm showing us an Excel spreadsheet which I've kind of coded to represent two magnets. So you can imagine the magnets over here. Red could be south and the green could be a north pole. And as you know, that if you put two magnets together, they will oppose each other. So, the north pole will attract towards the south pole, but if you have a north pole with a north pole, they will repel each other. And so what I've got over here is a simple solver, or so in Excel, I'm sure you're familiar that there's a capability of having a solver and you can put an equation in there and have it solve it. So if I was to make both of these magnets have the north pole, for example, the ones together, and we can imagine these north poles as a spin, kind of a spin up of a magnet. So we'll have the up over here, and then the zero can be the down over here, or you can say north and south. But you all know that if you have the north and north together, they will repel each other. And so in essence, they're not in the lowest energy configuration. And they want to move to the lowest energy configuration where one will want to flip. And so I'm going to use my solver to show you that. So solver is just a probabilistic tool. It's just trying out different combinations. And what it'll do is find, I've got a solution over here where it wants to go to the lowest energy. And so solver basically moved these to the lowest energy configuration. So I'm going to use that basic concept to show what could be happening with 5 qubits. So in here, I've got 5 qubits lined up, or in essence, there are 5 magnets in this representation. And I can change the configuration of these magnets, but as you can see that since the north will attract to the south or repel the north, this is the lowest energy configuration. If I have a north-south like this, then the next one has to be a south-north, and north-south, then south-north, and north-south, right? And if those magnets are together, then they will want to come into this configuration. So if I was to make all of these a 1, you can already imagine mentally that they're in a stress. They want to get away. This one wants to flip. They all want to flip into a configuration that will be of a lower energy. And you can kind of envision this strain as this energy has gone up, has gone to 4. and it wants to come down to the lowest value. So I'm going to do the same thing over here with my solver, which basically tries to minimize the energy of this configuration. And it runs for a few seconds, and I hope you're seeing this, but the results come back, and it's basically found a combination where it's at the lowest energy configuration, as you can see over there. So, we talk about in quantum computers, we talk about Hamiltonians, and Hamiltonians are energy equations. You can think of these magnets as having some kind of a magnetic energy, and they're wanting to come into the lowest configuration. So there are a few things I can do with these magnets. I can imagine a scenario where I move this magnet that's on top away from all the other magnets. And the way I can do that is by changing this influence. You could call it an influence, or how well this magnet is connected to the other magnets. So if I was to bring this coupling value, which is, I'm calling that the coupling value, if I bring that coupling value down all the way to 0, then this magnet in effect is basically not connected to the rest of them. There's no interaction between the magnetic field of this magnet and all the other magnets. And we can see that. So for example, if I make these all 1 again, now when I run this, they will, again, it will try to come to the lowest energy configuration, and we'll see how this one behaves. So again, this is probabilistic. So it did flip over, but it would have been, let's see, the energy value there is 0. And if I was to make this a 1, you'll see that the energy value is still a 0. So there really isn't much of an influence between this one and the next one. And maybe I'll show it with making some other ones 0 as well. So again, let's start with zeros over here. All right, so now you can see there's a bit of a strain over there. There's an energy of 2, and it's going to want to come back down to 0. But I've also disconnected the first magnet from the second one. These two are still connected together. And then the third one is disconnected. The fourth one is disconnected from the third one, and then these last two are connected together. So we'll try this again.
So does that mean the first one could be anything 1 or 0 without any coupling, without any pressure, if you will?
Yep.
The other,
yes, ideally
behaves on its own.
Yep. So again, it's probabilistic, so it will, it might be flipping it. Mm-hmm. But you can see that over here. So in this case, I started out with zeros, and this one remained a 0. Since solver does probabilistically try different things to see what combination works, it flipped this one. And since it flipped this one to 1, there's the coupling between this second and the third is at a 1. So it had to make this one a 0. So these two are opposing each other to have the lowest energy configuration. But as you can notice, it left this one at 0. So this doesn't seem to be affected. These two aren't being affected to each other or with each other. But since it left this at 0, it had to flip the last one to 1. So, just mentally you can see that there are, there's influences between these magnets which creates a higher energy configuration. And what this solver is doing is trying to find the minimum energy configuration.
So Alex, so like the last two, the bottom two there, number 4 and 5, it's kind of like, so the north of one wants to attract the south of the other one.
Yep.
And so that would be the lowest energy. And they would do that because you got the 1 there in the coupling, right?
That's correct.
Okay.
So now the other thing I can do is I can also influence some of these to be a certain value. So all of these values, I've got a 1 over here. And what I did is I'm calling it a bias, but what I'm saying is that I have no bias right now. But I can increase my bias so that I'm saying I want this one to be a 1. So, and we can try that out. So I'm going to make that a 1 and maybe even increase the bias over here where I'm saying I want this one to be a 1 as well. But again, there's no influence between these two. So you can see that this will probably try to make this a 1, but this one will just follow with the other one. So we'll see what solver does with that.
Yeah, so the first one should almost definitely be a 1 because your bias is 100% towards 1, right?
Yep.
Yeah, so that's almost guaranteed.
Right. So now because I basically made, the one bias is basically saying I want this to be a 1 and on this side. Now, since there's no influence to the second magnet, it's kind of being biased towards the 1 because of this equation over here, this bias over here of 0.85. And then since this has to be a 1, this obviously becomes a 0. And then these two are kind of random because there's no influence between the third and fourth. And so if this picked a 1 over here, this had to be a 0 over here.
So would you say that the bias is you're controlling that magnet, and so you're saying, like on the first one there, I want that to be a 1, and if you had flipped it over, if you had set the bias to be 0, then you're saying I want that to be a 0. If you put it 50%, then you're kind of indifferent. You don't care. Would that be?
Yep, exactly. So now this is not exactly how DWave works, but I wanted to get the purpose of this was to get the concept of biases and couplings out. So couplings are the influences between the magnets, or you can think of those as covariance terms or terms between the two magnets. And then the biases are somewhat of a strength that I want to have on the magnet itself. I'm pushing the magnet to be in a certain state. So those are the biases, individual biases. And then the couplings are the influence I want between the magnets. So typically, when we're doing these problems, we'll have different biases on the different qubits, which, I'll kind of represent those as biases on my magnets over here. And then we have different covariance terms, or they're also called quadratic terms. And those are the influences that happen between the qubits, or in my case, between the magnets. And again, those can be different values. And in my case, I'm using values between 0 and 1. But in the case of DWave, they go from -1 to 1. And you can have any value, but DWave will scale them down to -1 to 1. So if you can visualize, I've got certain couplings between these 5 magnets, and then I've got certain influences or biases on the magnets themselves. And I'm saying, you basically take the value of 1, and that's the amount of bias I'm putting to have that value as 1. Now, all of these are interacting with each other, and there is a solution to this. So, one can mathematically find that solution using linear algebra, or in the case of the solver, it will sample many different combinations and then find a combination that seems to have the lowest value. It might find the lowest value, which is called the ground state, or the actual global minimum, or it might find some local minimum value that's where it gets stuck. And those are called local minimums. So I'm going to run my solver and see if it finds a combination that works for it. And again, it'll flip these around to get to the minimum that it can. So as you can see, this is the combination it came up with. And basically, it wasn't able to get down to an energy value of 0. There's still, there's some strain still happening, but, this is the lowest value it came to. Now I can try to change some of these values. So this one was a 1, 0, 1, 0, 1. And I can try changing some of these values and trying again, because again, this is a random probabilistic type of a solver. So maybe it did not find the lowest value. So I'll run it again. And maybe this time it gets to some other configuration that's a little better. So I guess, that's the best one it found, and it's kind of stuck over there. So in a lot of our combinatorial optimization problems, which are, large, these problems where multiple objects affect each other, could be paths or relationships. In the case of assets, it can be the interaction between the assets. As the number increases, the relationships between those objects increases as well, and it increases exponentially. And these kind of problems are called combinatorial optimization problems. And they can be solved by linear algebra. They can be solved by various classical methods. Random sampling is one. There are genetic algorithms that can solve it. There are simulated annealers that can solve those problems as well. And DWave actually is a quantum annealing solution that is able to solve these problems through quantum annealing. So what I'm going to do is I'm going to shift gears a little bit. So I'm going to stop sharing this. And if there's any questions on that, I'll answer that. And then I'm going to get into a little bit of a presentation on how is DWave set up? What's the QPU look like? And we'll talk about those coupling and bias terms again.
So Alex, in the DWave then, the demonstration you just gave us with the magnets, the energy level in the DWave, is it calculated pretty much the same way by taking the various biases and the couplings and just, is it that straightforward where you just add those values up?
Yep.
At the end?
Yeah, I'll have to. So I'm going to show that DWave actually is. I think we'll have to get to the matrix that actually puts all of those values together, and it represents the Hamiltonian or energy of the whole landscape. DWave will find the exact energy. So when it's calculating, it actually calculates the Hamiltonian. It actually gives you the exact energy value. And then what it's doing, it's minimizing, finding a minimum for that energy landscape. And so that's a good question. And I will try to show that in my presentation in the slides as well. Okay.
Any questions from anybody else while he's getting set up? Anybody? Comments?
I did have a question. So on the initial state, when I think all of the magnets were south, or I think that's what 0.
Yep.
So when you set up the covariance between, I think, 2 of the magnets, and they flipped, I remember looking at it, and it looked like there were a possible five different configurations, because the first one was unlinked. So 5 different configurations that it could have stabilized into, but obviously it would stabilize into only one. But the probability that it would stabilize into any one of those 5, are they all equal, or is there any skew in the DWave system?
Should be no skew. If the energy value is exactly the same, then it can pick either one of those. I mean, it's equal probability.
Okay, I mean, for a single bit, I understand, but when you have linkages between bits, it's trying to minimize the energy, it's trying to optimize the equilibrium state. So, I mean, it does that perfectly. You're saying that the DWave system does that perfectly?
So, if you have this energy landscape and it has 4 minimums, right, and they happen to be exactly the same values, then DWave will, it will have to pick between those 4 values. So if you run DWave once, it will pick one of those 4 values. If you run it 100 times, then it will probably find those 4 values as the minimums majority of the time.
Okay, I mean, you kind of answered, that's what I'm getting at, is the majority of the time is, I'm trying to understand in terms of real world behavior, does it demonstrate real randomness as opposed to near real randomness?
So I mean, there's 2 different answers to that. So, I mean, DWave is a quantum computer, and if you were to, and it's not a gate computer, so if you were using DWave to produce a random number, that's more of something that you would do with a gate model. But inherently within quantum computing, and I'll show some of the diagrams, when it's in superposition, when you start DWave, you set it up in a superposition where all the qubits are in a 0 and 1 state, and they have equal probability of being a 0 and 1. So they can pick a 0, they can pick a 1. But now what you're trying to do is to find the minimum, you're trying to find that minimum energy configuration. So they will move towards that minimum energy configuration because of the quantum annealing properties.
So let's just say I had 2 magnets and I had the bias equal to 1. And so when the DWave starts, they're both aligned horizontally. And then we turn it on. 50% of the times it'll be north and north, and 50% of the times it'll be south and south.
Yep.
Yeah, but because the bias is 1, it'll only rest in the lowest energy state, which is where the 2 magnets are basically pointing in the same direction, thus the north and south connected between the 2 magnets.
Yeah, I mean, if it can go both north-north or south-south, then you will get 50% probability of those.
Yeah.
So I'm trying to figure out how to present my presentation over there. So do you, let's see, let me share this. Do you see the presentation?
Yes, it looks good.
Or talk about DWave?
Yeah.
All right.
Yeah. I think only I understand what that title means. It's time we talk about DWave, because a lot of people just ignore DWave, and so it's it's time we talked about sex. Remember that when you're like a teenager, your parents. So it's time we talked about DWave. Not to say DWave is sex. It's just, I'll leave it at that. We never talk about it.
Well, interestingly, I mean, that's the one I started out with. So, and they did create this hardware and made it available to a lot of people. So, I think people aren't talking about it right now because there's gate computers. But I think DWave is an interesting tool, and I mean that's the purpose of this presentation. So this first slide, I'm showing basically a circuit, and the way DWave works is, and actually any superconducting quantum computer works pretty much the same way. You have the special material, the chip that's made out of special material. When you cool it down to close to absolute zero, the material becomes superconducting. And so a current that is flowing inside that material has no resistance. And if you have a loop, which, this is a loop, the current has no resistance in going in either direction. So you, in effect, have a current that's flowing both in the clockwise direction and in the anti-clockwise direction. Now, if you've done, or if you remember your physics, a circulating electrical current produces a magnetic field. So, and there was the thumb rule where if you put your hand around the direction of your electric current, then your thumb points towards the direction of the magnetic field. So when current is moving in, let's say, this counterclockwise direction, you have a magnetic field pointing upwards, and you can call that as your spin direction is up. And you can represent that as a 1 or a plus 1. And then you have you also have a current moving in the opposite direction, in the clockwise direction, which generates a magnetic field or a spin that's pointing in the downward direction. And so it's this property that is being used to create you would call it like a virtual qubit. It's not an actual atom that is spinning up or down like an electron spin has a spin property of up or a spin property of down. This is an actual circuit that is using superconducting material to allow current to move in both directions. And since the current is moving in both directions, you in effect have both a 1 and a 0, or an up and a down influence happening at the same time. Now, this thing is actually called, starts with the word icing, and the spin up and spin down are generally referred to as a +1, and then the up is +1 and the down is -1. But then that is translated into DWave, where if you're dealing with binary numbers, you can also convert the +1 to -1 to 0 to 1. So for our purposes, we're just going to use binary and not icing. We're going to use up as 1 and down as 0. All right. So the way this circuit is controlled is by having some other circuits or inductors and capacitors over there that control the effect of the current that's flowing, and they connect these. So this is basically a qubit with both a 1 and 0, and it's connected to other qubits. Now, one of the critical components is called the Josephson junction, which actually allows this to work. And so I'm not going to get too much technical in there, but that's a critical component there. All right. So how is this circuit inside the chip? So this is an image of the DWave chip, and this is a component which is basically looking at 8 qubits. And the way the qubits are lined up is they're in vertical and horizontal configuration. So you've got 4 qubits that are in verticals over here. They've only shown 1. So there's 4 vertical qubits. And then you could think of those as columns. And then there's 4 horizontal qubits where the first one is shown. And then there's 4 underneath that. You can think of those in rows. And so there's 8 qubits over here, and they're overlapping each other in certain places. And where they overlap is where you can influence the, one qubit to the other qubit. And so that's where the coupling comes in between the qubits. So you've got, these 8 qubits, and then they've got certain places where there's coupling between them. And that's where the qubit interacts with another qubit. All right. Now, again, when you're actually working with the qubits, you're looking at, you're looking usually at a graph diagram like this, and they represent, so the qubits are grouped in these 8 units, or units of 8. And so basically over here, they're showing this unit 1, 2, 3, and 4. Each one has 8 qubits in it. And there is interconnectivity between the qubits inside. So each qubit is connected to about 4 qubits. And then there's some connectivity between one unit and the next unit with the red lines, so with the red curves. And those are connections between one set of qubits to the next set. And there's some representation of it over here as well. The key point is not every qubit is connected to every other qubit. There's a maximum of 4 connections internally, and then there's one going outside on some of the qubits. For example, you can notice that the one up on top over here isn't connected to the one over here at the below it. And we'll go a little deeper into this. So now I'm only showing one of those units of 8 qubits. So each of the qubits is given a number, 0, 1, 2, 3, 4, 5, 6, 7. And there is a connection from 0 to 4, 0 to 5, 0 to 6, 0 to 7. But there is no connection between 0 and 1, 0 and 2, or 0 and 3. So you can see there's about 4 connections between one qubit and the other. But then there's some qubits that are not connected together. So when we were talking about magnets, I had the magnets all lined up vertically. And there was connections that were there was only one connection between one magnet and the next magnet. It was basically a linear arrangement. Here you've got a 2-dimensional arrangement, but there are limited connections between those qubits. All right. This representation is also shown in this cross diagram or diamond shape. And you can see that the qubits have just been rearranged, but they represent the same as the column diagram over there. So you can see the connection between one qubit. Sorry, I'll start with qubit 0. So qubit 0 is connected to qubit 4, 5, 6, and 7. So it's an equivalent representation, but it, I think, spreads it out a little better so you can see the links. This is important because when you go into DWave, you can actually inspect how your circuit is, how your problem is embedded on the hardware. And that representation is in a diamond, in this diamond form. So it's good to know that. Okay, so as we said that, the minimum energy of 2 magnets is basically, 0 and 1 together. So what I'm showing in this diagram is that in this loop, which, the SQUID loop, you can have a 0 and 1 energy. You can have both 0 and 1, and that is the minimum state for a qubit that's in superposition. Now, the way DWave works is it changes the energy landscape. So for example, if I wanted this qubit to end up in a 1, I will start raising the energy of the 0 so that 0 has a higher energy and the 1 has a lower energy. And so in the end, DWave will want to go towards coming out with 1 as the answer. It will not prefer the 0, it will prefer the 1. Okay, and so a little bit of a comparison between classical annealing and quantum annealing. So in classical annealing, classical annealing is a representation of like a thermal process, and it's mathematically simulated as if a thermal reaction was taking place inside a material. So as time goes by, basically what they're doing is they allow random sampling or random fluctuations of a solution. Just like in the solver, I basically use a random sampler which basically tries out different combinations, and it keeps track of the minimum, and then in the end, whatever minimum it comes to, that's the configuration it picks. So in classical annealing, you start out with some location, and then you pick different values. You just randomly pick values close to this. In the beginning, in effect, when your temperature is high, you will pick values that are considerably far away from that original value. So you might find a value here, then you might find a value here, then far away. And by doing that, you can jump through high energy configurations and find some other one that is a lower energy configuration. And so with classical annealing, you're able to find a minimum because you might start here, but you won't get stuck there. During the annealing process in the beginning, you will jump around and look for other values. And if those look better, then you'll go into those. But as time goes by, your temperature goes down and you're not jumping around as much, and your fluctuations get less and less. So eventually, you're just going to come down to the minimum. So it's not gradient descent. So for those who've done gradient descent as a way to find the minimum value, in quantum annealing, it's kind of it's a simulation of a thermal process. In quantum annealing, it's totally different. You start out with all of your qubits in superposition. They are at the lowest energy configuration. And then you put in those biases and coupling terms where you are changing the energy landscape. Like I said, you're stressing the system. You're wanting it to go. It wants to go into its lowest energy configuration. But you're relying on the fact that in quantum in quantum mechanics, there's a property called tunneling, where quantum fluctuations will automatically go through high energy configurations. So again, it's somewhat of a similar process where you start out with a high amount of quantum fluctuations where DWave can go pretty much anywhere. But then as you do your annealing process, it will eventually settle into lower energy configurations through quantum fluctuations that use this tunneling property and are able to find, the theory is that they're able to find a more global minimum by going through this tunneling process. I put names of Ed Fari and Hidetoshi Nishimori. Hidetoshi Nishimori actually came up with the theory of quantum annealing, where he proposed that through these quantum fluctuations, it would be possible to make a system that would be able to do something like simulated annealing, but using quantum computers. And they proved that for certain problems, quantum annealing would have theoretically better results and faster results than simulated annealing. And then Ed Fari also was instrumental in writing papers and then working with DWave, to get their system up and going. So both of these people have quite a few papers out there on annealing and adiabatic annealing. Basically, the key theories used by DWave. All right. So when we put a problem onto DWave with all, let's say there's, in this case, they're saying 500 qubits and there's 2 to the 500 possibilities, the landscape looks like, looks like this. There's many peaks and valleys, and there are many 2 to the power 500 different possibilities of answers. And the question is, can the D-Wave system then find a minimum in this landscape? So as you can see in this landscape, where the ice is accumulated, or ice or lakes, those are the minimum energy locations. And one of them would be the lowest energy, or the global minimum. And the real challenge for quantum annealing or classical annealing or gradient descent or genetic algorithms is to find this minimum in a huge landscape like this. And that's what D-Wave does. I have put some links over here to some papers, videos that would be interesting. Some of them are very complicated, but if anyone wants to look at that, they can look at it. Okay, so I'm going to stop sharing the presentation. Any questions so far? I'm going to actually get into D-Wave and show the code.
Hi, Alex. Thanks for your presentation and spending some time with us on this.
Sure.
Trying to figure out how to ask this question so it makes sense.
Sure.
So I'll try to dive right into it, I guess. So I've heard this is probably more from people associated with the gate circuit kind of computers. I've heard claims that, well, D-Wave isn't really a quantum computer. It's this annealing thing. And I also understand that there's at least the number of qubits in D-Wave machines are something on the order of 1,000, and they're working on a 2,000 qubit machine, something like that. Can you help me understand that a little more of the differences between the annealing approach versus the gate approach, and then what's so different about the qubits that you can put 2,000 qubits into a D-Wave machine, but state of the art for a gate circuit is something on the order of 70, I think.
Yeah, or 100 or something. Yeah. So first of all, inherently D-Wave is only trying to minimize the energy. And so if you look at quantum mechanical properties, D-Wave is using the circuit, or the quantum circuit, which is using regular CMOS technology, and they've basically got a superconducting circuit, which is, these things are, easy to make because we already have CMOS manufacturing equipment. These are not real atoms, unlike ion traps or something like that. So first of all, D-Wave has a CMOS technology and was able to use that to create superconducting qubits. And all it's doing is letting quantum mechanical properties of let the qubits reach their minimum configuration naturally. And of course, the work in there is, of course, with controlling the qubits, putting the right biases on it, and evolving it properly, letting it have those quantum fluctuations and quantum tunneling properties and all of that. So I'm sure, again, I was not involved in this. I'm not part of DWave, but a lot of technical and engineering challenges would have taken place in, trying to figure all of that out. In the end, though, DWave is minimizing the energy landscape. It's like a single purpose tool. Now you can do many different problems with it, but it solves this problem. It solves a minimization problem. And that was the purpose of my presentation also, to show you that, it is really, you can think of it as magnets reaching their most appropriate or minimum energy configuration. That's what's happening at the qubit level. So to make that kind of a circuit and get to 2000 qubits, so the current DWave system that I have access to has 2041 qubits, and they were able to create this chip that does that. Gate computers or universal computers aren't just minimizing the energy landscape. They are trying to do, gate logic. And so they are, in effect, using very different quantum properties and then manipulating those properties to do logic, to do additions, to do various quantum algorithms. So it's a much more complicated problem to solve, and also to manipulate the qubits, to track the qubits, to make sure that they follow, they actually follow the algorithm the way it's supposed to be followed. So it's a dramatically different problem. Now, you mentioned that, some people say that DWave isn't a quantum computer. I would challenge the fact that, it's all kind of like semantics. These are, both IBM and DWave use chips, and they're simulating quantum properties using this SQUID circuit, which has got opposing superconducting current and spin. They're not really using an electron or, like in nitrogen vacancy centers, using atomic properties or energy levels to simulate the qubit. So in essence, it's a virtual qubit. It's kind of a simulated qubit. But they're using quantum properties, so they are both quantum computers. DWave is more for minimizing the energy landscape only, while something like IBM is for actually doing gate operations or logical operations, which makes it more complicated. And in the end, however, when you go to ion traps, like IonQ has an ion trap, Honeywell has an ion trap, they are actually using real qubits. So, and they're doing gate calculations, so there would be more quantum computers. So, so that's kind of my answer.
That helps. Thank you.
Sure. Okay, so somebody asked if are these thousands of logical or physical qubits? So the DWave 2000Q has 2041 actual hardware physical qubits. They have the new architecture, which has come out. I just don't have access to it, which has 5,000 qubits. Those would be 5,000 physical qubits. On the other hand, so when you say logical, the question would be, for example, so I'll get into that as we go into the embedding. What happens is, because every qubit isn't connected to every other qubit, in order to make use of the connections, if I need more than those 4 connections or 4 links between qubits, I have to spread my qubit onto multiple qubits. So my problem qubit, which you could call, let's say, a logical qubit, has to be spread onto 2 or more physical qubits. And by the time you get to a 60 qubit problem, because of the lack of connections between the qubits, you could have one logical qubit spread over 7, 8, 9 physical qubits. I don't know the correct answer for the error correction. Obviously, internally they have to do some error correction and get the best energy values. In all of my usage of DWave, the energy value that I get back is exactly the same as the value that I would get from a classical calculation. So I'm sure there was some error correction involved over there. It's not the error correction that you would think about when you're talking about gate quantum computers, which have a lot more error. And a way to think about this is you're trying to hold, in a gate model, you're trying to hold these qubits in configurations that are not the lowest energy configuration, and they will be influenced by the outside to, they'll bump against the outside in the sense that, microwaves and other magnetic fields can hit them, which will eventually cause them to decay into their lowest energy. But a gate operation requires them to stay in these high energy configurations. So error correction is very important for gate computers because you're trying to hold those qubits in the energy you want them to be at. On the other hand, with DWave, anything that would move it towards this lower energy is great, right? So the qubits will naturally go down to the lowest energy. All right, does anyone know what? I don't know the exact number for the connectivity. I've heard numbers like 12. Each might be connected to 12 others, but I heard that somebody mentioned it. So I don't know what the actual number is. Someone at DWave would know. All right, so we're at 8 o'clock, and I'm going to get into the code and kind of just show really quickly how this code is implemented on DWave. Okay, so you should be seeing the DWave environment, and Daryl, are you seeing the
Yes, we can see
DWave
it.
environment? Okay.
Yep.
All right. So again, for those who've never gone into DWave, of course, you have to sign up for DWave, and then after you get into DWave, you can create your own environment. So I basically have a DWave environment set up. I've moved some code into it, and you can link a GitHub. You can link your GitHub URL to DWave, so DWave will pull from GitHub. In some cases, at least with my account, I can do that. So I've got the code over here. I've got my browser over here, looking at the different files in there. I'm only going to focus on this DWave starter code version 5, which you can see over here, and go over some of the key components of it. In the beginning, I've got some imports going on. I've got a DWave sampler that I import. There's an embedding composite. Again, the embedding composite basically takes your problem and then puts it onto the actual physical hardware. And got some extra things in there. I also have the DWave inspector, which I will use to look at how was my problem put onto DWave. So I also have in here different files. I'm going to open up one of my files. So q3.csv is basically a matrix, and it's basically representing, you can imagine like 3 magnets, or in this case, could be a problem with 3 elements. And so it's a 3 by 3 matrix. The linear terms, for those who are familiar with linear algebra, those are the diagonal terms over here are the linear terms. So from the top left to the bottom right, that's the diagonal. Those represent the biases that I was talking about. So the bias on the qubit is represented in the matrix in the linear terms. Are called the linear terms, and they're represented on the diagonal. The interaction, so for example, this is a 0, 1, 2, so that's my 0 qubit bias, my 1 qubit bias, my 2nd qubit, or 2 qubit bias, which is my 3rd qubit. Then I've got terms that are the covariance terms, or the coupling between my qubits. So the coupling term between my 0 and 1 is this term over here, negative 0.428. The coupling between 0, which is the first row, and 2, which is the 3rd column, is negative 0.426. And so you can see over here, the one I'm highlighting, well, I'm sorry, I think this is probably not big enough. So this value over here, 0.445, would be the coupling between 1 and 2 is over here. Now you can see that the right side of my matrix has a mirror image on the left side. So in a matrix, you have a mirror image on your 2 halves of your matrix, but DWave is really only looking at one side of the matrix. It only really cares about the coupling between the terms. It doesn't need to have that information again. It doesn't care about, actually the coupling between 1 and 2 has to be the same as the coupling between 2 and 1. They can't be different. So this is what I'm reading in. And so it's a matrix. I read that in. So I'll go back to my code over here. All right, so in this code, I've commented out a part where I would randomly generate the matrix, but in this case, I'm just going to read it in from Q3. I find out my length, which is going to be a length of 3 for this matrix. I pull out my linear terms. Those were the terms on the diagonal from within the matrix. You can see they're linear because I'm pulling out, as I go through range K, from this matrix Q, which I pulled in here. Those are linear terms, so there's Q, K, K. So Q00, Q11, Q22. And I'm basically adding those into a dictionary, which basically says A0 has this value. Then A1 has another value. A2 has another value. And those are my linear terms, which I just pulled out from the matrix. Then I'm building the quadratic terms, which are tagged as A01, and it would have a value pulled out from the matrix. I do it for 1/2 of the matrix, and the way you know that is this J is less than I plus 1. So as I go through both I and J, in range dim -1. I'm only going through 1/2 of that matrix. And so this basically makes the quadratic terms A01, A02, A12, A01, and so on. So I've got a dictionary of my linear and quadratic terms. I put those in QDWave, and I'm going to print out QDWave so you can see what that looks like. I have a chain strength of 1. Chain strength is not really relevant right now, but when you have 1 qubit spread over multiple physical qubits, then the chain strength becomes important. Number of runs is how many times I want to run DWave. If you write only once, you will get a value, but typically doesn't end up being the minimum value. So we will sample DWave multiple times on this problem. Okay, so then embedding composite takes my problem and maps it to the hardware. And then you take all of this stuff and you put it together over here with sampler, sample, QUBO. QDWave is that QUBO formulation, which was in my dictionary, QDWave. I've got a chain strength, I've got the number of reads, and then that will create a response. And then I will basically print out the response. So I'm going to run this. I have this DWave inspector over here as well. So what will happen is as it runs through the code, it's going to print out the solutions at the bottom over here on my terminal, and it will show me the embedding. So I'm going to run this. Okay, I'm going to do this one more time because I want to make sure I can see these values. All right, just a second. Okay, well, we'll just, all right. So what I'm showing over here is that my problem was basically using up 3 qubits. Those are my 3 qubits. And here they're being shown in a graph with 3 vertices and 3 edges. And you can actually see the values that are being put. So 0.44 is the coupling between qubit 1 and 2. Negative 0.42 is the coupling between qubit A1 and A0. And then this is the coupling between A0 and A2, negative 0.4. So, you know, that's pretty straightforward. And then you can see over here, and actually I'm a bit surprised, but let's see. I'm using up 4 physical qubits. I'm going to make that a little bigger if I can. So in this diagram, you can see I've got 4 physical qubits being used to represent 3 qubits. And that's what the embedding came up with. I mean, every time I run the embedding composite, it comes up with a different embedding. So here's A1, A2, A0, A0. So this is again A0, A0. So these 2 are representing the same qubit put on 2 qubits. And then here's A2 and here's A1. And so the couplings between these couplings over here will represent the coupling that we had, but the coupling between the A0, which is spread into 2 qubits, this is called a chain. And the bias over there, you can see, well, the strength of that coupling is dependent on that chain strength that I put over there as 1. So basically what it's saying is that I have to be able to hold the same value in both of these because they're representing the same qubit. If one became a 0 and the other one became a 1, obviously that means that my problem has messed up. And so your chain strength has to be the right value to maintain that. Okay, so that was just the embedding. I'm going to remove that. Want to show the actual output over here. Make sure everyone can see it. Okay, so I'm going to start over here. So I ran the code. I printed out the matrix, which is this part. You can see the linear terms and the quadratic terms, the linear on the diagonal, quadratic on the sides. Then I built the Cubo formulation of this matrix where I put the linear terms and the quadratic terms. So here's the A0, negative 0.489, A1, 0.31, A2, 8.8. Then A1, A0 is negative 0.428, A2, A0 is negative 0.4, A2, A1 is 0.4. So this is the representation of that matrix that actually goes into DWave. You can actually use other ways of converting your matrix into this Cubo form. There's all kinds of different functions available in DWave to do that. There's all kinds of embedding functions to do all kinds of, some embeddings might not be as efficient as other embeddings. So there's all kinds of different embedding composite functions. And then you can see the answer over here is 0, 1. So 0, 1 has, so in other words, the 0 qubit and the qubit 0 and qubit 1 are both 1, gives an energy value of negative 0.601, and that showed up 7 times in my 10 samples. And then qubit 0 being 1 showed up 3 times with an energy of negative 0.489. So the way DWave generally gives its results is, depending on the number of samples you do, it will accumulate all the similar answers, and the lowest energy comes up first. So this is my lowest energy value of negative 0.601, and it sampled it 7 times. And then the next energy value was 0 as being plus 1, and then 1 and 2 were 0. And that has an energy value of negative 0.48, which is, slightly higher energy value, and it sampled that 3 times. So again, this is a very simple problem. And I call it my starter code. So for those who are interested, they can get a copy of this or request a copy of this. Okay, so I think we're at time. I'm going to stop here, see if there's any other questions.
Now's the time, people.
I did have a question. So the energy values, that part's confusing me because energy values are negative. What do the energy values represent in terms of real world?
Okay, great. Actually, that's a good question. If I may, I need to show a diagram of a bigger matrix. All right, so this could go into, all right, I'm going to share the screen. All right, so I'm sharing an Excel version of a matrix. So you can see the linear terms are on the diagonal. They show up in red over here because in this example, these are all negative values. And then the nonlinear terms are positive. Most of them are positive, and they are spread on the left side and right side of the matrix. Okay, so what I want to show from this is, and please ask me questions if this is not very clear, but if I start out with a matrix, this is a 20 by 20 matrix, all right? When I say, what is my lowest energy value, what I want to show is how that really works. So I'm going to make all of these 0. And I'll explain what this really is. Okay, all of these are 0. What was happening in the case of the magnets is similar to what's happening in the case of DWave. Basically, we're picking different combinations, right? So if I was to pick only my first qubit, qubit 0, if I only pick qubit 0, I'm going to pull the linear energy value that was on that qubit, which is the bias on that qubit. And you can see I've pulled a negative 0.49. If I go back over here to my matrix, for the 0 qubit, it's negative 0.49, right? That's the linear term. If I only pick one qubit, my energy value will be only that linear term. Now, that gives a value. So I'm going to sum all of these, and my total energy value is negative 0.49. Now, let's say I sample and I pick another one over here. I'm just going to pick qubit 6. Okay, so now I've got 2 qubits. When I pick 2 qubits, I have to pick both of their linear terms. So the bias on qubit 0, bias on qubit 6, and I sum them up. My biases end up adding up. So negative 0.49 plus negative 0.66 is negative 1.16. So that's the sum of my linear terms. Now, in addition, since I picked 2 qubits, I also have a coupling between them. That term shows up over here. So my coupling term of qubit 0 and 6 is 0.169. Since I picked those 2, I have to add the quadratic term. So the ones that are not on the diagonal are called quadratic terms. That is the coupling effect. And that happened to be a positive number, so I'm adding up 0.169. So that's adding over here, 0.169. Then I sum up the linear terms and the quadratic terms. By the way, those are mathematical formulation for that. And then here's the sum of the linear and quadratic terms, negative 0.994. And in effect, what you're doing is you have an objective function where if you pick different qubits, you will get different energies. And you're trying to find a combination that has the lowest energy. Okay? So let's say I was to pick another one. Let's say I'm going to pick 12. All right. So when I pick 12, I add up 3 linear terms. Negative 1.638 is the sum of that. And I pick up 3 of the coupling terms. So with 3 qubits, in my example with the 3 qubits, there's 3 linear terms or 3 biases, and there's 3 quadratic terms or the 3 covariance terms or the 3 coupling terms, and those get added over here. So I've got a positive value, and I've got 2 negative values. They add up to negative 0.98. And now my total of the linear and quadratic terms is negative 2.6. In effect, what DWave is doing is finding the combination of the qubits, which when turned to 1, will have the sum of the linear terms and sum of the quadratic terms be the minimum. I actually have solver on this as well. So I'm just going to run solver to show you. So I'm going to go to my solver, run solver, and solver is doing the same thing. Now it's dealing with 20 by 20 matrix. It's going through and trying out different combinations and keeping track of the minimum energy through the summation of the linear and quadratic terms. And then it's going to show what is the, the minimum value that it came up with. So it found a minimum of negative 7.29 using this combination of qubits. So qubit 0 and 1 are positive 1, 2 is 0, 3 and 4 are 1, and so on. So this is the combination that gave that minimum value of negative 7. Now, again, this is solver. If I ran solver again, there's a good chance it would find another value. It could go lower than negative 7. It could go higher. But after sampling many times, you begin to see where your minimum is, and you begin to see which of these qubits will create that minimum. So I think that was a long answer, but this is an important part to keep in mind. DWave is basically adding up linear and quadratic terms. And if you think about the term QUBO, quadratic, unconstrained, binary optimization, that's what this is. This is a quadratic model. It's unconstrained in the sense that there's no constraints on it. It just needs to add up the terms, the linear and quadratic terms. It's binary because your variables that you've got are either 1 or 0. So you're going to get either a negative 1, positive 1 in the icing model, or 0, 1 in the binary model. And then it's optimizing it. It's finding the minimum of that, and that's what the QUBO is. Okay, any other questions?
Just one other question. It's me again, sorry. So how can you be sure that you reached the minimum energy configuration?
Well, that's another excellent question. How much time do we have? If you don't mind, I can show what I do to find the minimum. So while I'm bringing this up, for small problems, obviously, finding the minimum is not difficult. You can use a classical method to find the minimum. As your problem space increases, as your number of qubits that you're going to be needing increases, it does become more and more challenging. So before I get into that, so basically you can use classical methods to find your minimum, because it really is an addition problem, right? You're just adding up your linear and quadratic terms. You can try all combinations. In other words, if you have 2 to the power n different possibilities, you can try all of them out through using a binary addition. You can start out with 0001, then you go to 00010, 00011, 0000100, right? You just have a binary counter, and you can go through all of your combinations and then keep track of your minimum and find your minimum that way. As your problem space increases, your that method of finding every possible answer will not work because you run out of time. That method obviously is called brute force. By the time you get to 2 to the power 60, for example, or 2 to the power 30, you're dealing with trillions of possible solutions. And to go through all of that takes a long time. So I did 2 to the power 20 using solver in Excel, and it was using an evolutionary solver. So it didn't sample everything. It just went and sampled. It started with the seed and it sampled, and that did an evolution. I'm not sure if it's genetic or not, but it's some kind of a genetic evolution. Now, as your space increases, and that's the real concern, you can get to a point where you might not know what your real minimum is, because classically you just can't find it. There are obviously sophisticated algorithms that you can use, like genetic algorithms, that can find the minimum. And you can use elastic compute, like in Amazon, to use all kinds of resources to speed up and do a lot of computation. You can use parallel processing in supercomputers, but there is going to be a point where classically we'll just not be able to get to the real answer. So anyway, I'm gonna run. I'm running basically the same code that I just showed in DWave. I'm going to. It's just in Jupyter Notebook. I'm going to pull in my 20 qubit CSV file. In fact, I'm going to print it so you can see it. This actually happens to be the same data that was in that Excel spreadsheet. So this is a 20 by 20 matrix. It represents exactly the same that was in the Excel spreadsheet. I'm going to run it through DWave. I'll do 1,000 samplings of it. Chain strength of 1 is going to create a QUBO. It's going to run it through DWave. And when this asterisk, turns to a number, DWave has given me a result. I can print out my result. And so the result from DWave is 0, 1, 3, 4, 6, 12, 18, and 19 are 1. The rest are 0. And the energy is negative 7.2996. Now, DWave, I sampled DWave 1,000 times. I sampled DWave 1,000 times, but I'm not showing all my 1,000 results. I'm only showing my best result, which happened to come out 28 times. Okay, now to answer your question, I have this probabilistic sampler over here, which is a way for me to, I ran this earlier, so that's what the landscape looks like. But I'm going to run it with a different number just so I can see a different landscape. So what this is showing is what I do in this probabilistic sampler. I sample one qubit answers, then 2 qubit answers, then 3 qubit answers, then 4 qubit answers, and so on, up to 20 qubit answers. But I don't do it using brute force. I don't sample everything. I basically sample a certain number within each of those. So what this is showing is that my lower number of answers, so in other words, if you look up here, if I pick 11, 1, or 13, or 18, these are only 1 qubit answers, right? Only 11 is 1, the rest are 0. Only 1 is 1, the rest are zeros. These are my energies. -4, -0.5, -0.7. Then I select, and every time I get a better answer or lower energy, I'm printing it out over here. Then I try 2 qubit answers, 13 and 18. And again, these are random samples. Doesn't sample everything. 13, 18 gives a -1. So this was better than the last one. Then 1, 14, -1, better than the last one. So it's only showing when I get a better value. So as I go forward, this answer with 0, 1, 2, 3, 4, 6, 10, 12, 18, 19 had -5. So the best energy value I got from my probabilistic sampler was only -0.5, while as you see DWave gave a -7. Now I can increase this to more sampling, which will take a little longer, but in the end I will probably come up with something closer. So now it came up, you can see more values in here. The minimum, you can begin to see where those minimums are in this graph. So anything that's, those lines that you see coming down, those are the minimums, somewhere in 10, 8 to 12 qubit answers. So those are the minimum energies that we're looking for. And there's a good way of visualizing your landscape because, you can have very high energies as well, but there are these minimums that we are looking for. And you can see that kind of goes in a U shape. So somewhere over here is the best value. And the best I found was -6 using my probabilistic sampler, which does a lot of calculations, is doing 1,000, up to 1,000 samples per number of qubits. So it did 15,000 samples out of a possible, whatever this number is, 1 billion, 1 million. Yeah, 1 million. So that's one way of validating and verifying what does your landscape look like. Obviously, you might not be able to see the whole thing because you just don't have enough time to see everything, but you can get an idea of it. And then DWave generally does a good job of finding the minimum. And I had 1,000 samples done over here, so it gave me a good energy value. If I'd only done 10 samples, I would not have gotten a -7. I would have probably gotten a -4 or something. Okay. So I'll stop sharing that. All right.
All right. So have we just added 20 more people to the stable of DWave developers out there?
Yeah, it's easy to get onto DWave, and once you know the basics, I think this was the hardest thing for me to understand.
I agree.
Okay, so I've got comments over here about the ground state. Anyone used to DWave in locating the ground state or minimum of a molecule? I don't think it's possible to use DWave to find the ground state of a molecule because electrons and nuclei can't be modeled by a simple Ising model. So there are papers out there that for simple molecules, there's one I think that goes up to, there's hydrogen, lithium are simple ones that have been done by both gate models and DWave. But I think there are more complicated molecules that have been done with DWave because it has, 2,000 qubits, and I'm sure they've done more with the 5,000 qubit. But if you represent your molecule in a Hamiltonian, so in other words, you look at the positive charge of the nucleus and your electrons, and you create the Hamiltonian of your molecule, which is, you know, the energy configuration, then you can put that Hamiltonian, you have to convert that Hamiltonian into a QUBO. And then you can use that QUBO and find the minimum energy of that QUBO, which will give you the minimum of that molecule. So it is very much possible to use DWave to find the minimum energy of a molecule. And there's many research papers out there that have shown that. I think the more important question is, does DWave find the minimum ground energy? Is DWave capable of finding that ground energy? Since it is an annealer, there are a lot of theoretical considerations in finding that minimum. And I don't have time to get into that right now, but how you evolve DWave through the annealing process and how close the ground energy is to the next energy level are all factors in where, as you evolve, if you evolve too fast and your gap between the minimum and the next energy level is too close, your DWave will jump into the second energy level or the higher energy level. So as you go through that evolution, it will never then find the minimum. It'll find a good answer, and we get lots of good answers with DWave. And actually, sometimes if you don't care about the best answer, DWave can give you a lot of good answers. But with the right tweaking, with the right embedding, with the right timing, it is theoretically possible to find the minimum energy state of a Hamiltonian of a molecule.
Okay, last call. Anybody else?
Any other?
Alex, thank you very, very much.
All right.
Great job, indeed.
So I'm sure this video will be available, and Terrell, I'll give you the link to the GitHub page where I've got all of these samples.
Excellent.
So you can, you can share the video and share the GitHub link, and it has the presentation, the Excel spreadsheets, the sample code, the Jupyter notebook, all of it is there.
Okay. Well, thank you on behalf of everybody here tonight and all the future people that will watch your video. It's a good lesson. Thank you very much. All right, everybody. Much appreciated. Good to see you all. Apologize for the snafu with the link. I think I know what happened behind the scenes here. We'll get that solved for next time. Alex, thank you very much. And
you're welcome.
Good night, folks.
All right. Thank you, everyone, for spending.
We'll see you next time.
All right. Goodbye.